Okay, let's talk about applications of derivatives. The last section here is called differentials, which might be an intimidating sounding vocab word, but what we're really doing is just using the tangent line to approximate the function. Remember, we're calling the tangent line to be the best linear approximation to a function at the point of tangency, so now we're going to see just how to use it. So let's talk about the tangent line in general. The derivative is the instantaneous rate of change of a function, and we can think about that as the slope of the tangent line. The tangent line is the line that goes through that point and has a slope equal to the function's derivative, instantaneous rate of change. So symbolically, if you have the graph y equals f of x and a given point, x naught, y naught on the graph, if you have f prime equals m, then the equation for the line in point slope form is like this: y minus y0 equals m times x minus x0. And that should be something familiar. We've already done that in Unit 2. So if we want to use a new form to write this down, instead of writing y minus y0, that's really delta y, and x minus x0, that's really delta x. So here I'm using these squiggly equal signs. If you think about this equation as talking about points on the graph y equals f of x, it's not exact, right? F prime of x naught is the limit of delta y over delta x as delta x goes to 0. But anyway, if delta x is small enough, then this approximation will be fairly accurate. Another way to write this down instead, you'll see this in all sorts of textbooks, dy equals f prime dx. So this is called a differential form, and the dx and the dy, it's not d times x and d times y. This is one variable, dx, and it's called the differential. It's supposed to stand for infinitesimally small changes in the variable, but in practice we will give some value, some non-zero value to these variables. Okay, so suppose you want to approximate the value of a function, let's say by hand. So just as a quick example, what is the cube root of 130? So you guys could probably at least get a rough guess in your head if you know that 125 is 5 cubed. Okay, so we want to think about the cube root function, and we want to use the known value that the cube root of 125 is 5. So starting from there, we also know the derivative. So f prime, right, using the power rule, 1/3 x to the minus 2/3 power, plug in 125 for x, and you get f prime is 1 over 75. Now we're going to write down the differential form. So dy is f prime times dx. And if we're thinking dx is the difference from the known point, 125, to the point we're trying to estimate, 130, so dx equals 5. So we know f prime, we know dx, so dy is 1 over 15. So our estimate y value is 5 plus dy, and that's 5.0666 repeating in this case. And if you want to compare that, the true value on a calculator would be 5.0658, so okay, we can also use the tangent line to approximate the solution of an equation. Here's a cubic equation, x cubed plus x squared plus x equals 100. If you don't want to use the cubic formula, if you just need an estimate, this is really nothing that is applicable in modern life, but understanding these techniques will tell you basically how modern numerical methods work on computers. So how do we solve this equation? Well, we'll think about the function f of x equals x cubed plus x squared plus x minus 100. We want to find a 0 of this equation. All right, so the first guess that comes to mind, x equals 5 is going to be way too big. F of 4, this is a typo. It should be 84 minus 100. So f of 4, let's see if I can write this out using the mouse, minus 100. So f of 4 is minus 16. Kind of looks like a angry ghost. So if we look at the differential form, dy equals f prime dx, and we set x equal to 4. Now f of 4 is negative 16, so we want to set dy to 16, so we can increase up to 0. If you do that and plug in those two values, then you can solve for dx. It should be 16 divided by whatever we get when we plug in 4 here, so that ends up being 57. So dx is 16 over 57, and now we can check our estimate. F of 4 plus 16 over 57 is 101.05, again, minus 100, and that's a much closer to 0 than the original. Now, if you want to do even better, then you could just repeat this process. I'll have to move the video here. If you start the same process again, but with an initial guess of whatever your answer was now, so 4 plus 16 over 57 as a guess, you can again calculate dy over f prime and have a new dx and get a new guess. You can iterate this as often as you want, and it'll approach the accurate solution very quickly. This process is called Newton's method. It's the section in the textbook that we skipped, 3.8, I think. So you should know how to do the one-step approximation, but don't worry about writing down formula for Newton's method for more than one step. Okay, the last application to differentials we want to talk about is propagation of error in measurement. So again, it's easiest to talk about an example. If you want to find the volume of a sphere by measuring the radius, well, suppose that your measurement of the radius is only accurate to 1/10 of a centimeter, to 1 millimeter. How accurate is the volume calculation? So let's write down volume as a function of radius. Volume is 4/3 pi r cubed. We know that. And if you plug in 10 for r, we can get a value for the volume, 4,188.8 cubic centimeter. So how accurate is this? Well, let's look at the differential. So dv is 4 pi r squared dr. And here we're going to say dr is our error in measuring r. So I could have over or underestimated, so dr is plus or minus 1, which means plug in 10 for r and calculate. dv is plus or minus 125.7 cubic centimeters. That's the error in measurement. So usually the raw error, we don't really know how to interpret this number, but if we interpret it as a percent error, it'll give us a handle on how large this is. So the percent error is dv divided by v times 100%. In this case, it's approximately 3% error, and it's instructive to compare that to the percent error in radius. So dr divided by r, 1/10 of a centimeter divided by 10 centimeters, so that's only a 1%. All right, so the error in volume measurement almost triples compared to the error in radius measurement. And that's how, when you have nonlinear equations, nonlinear formula, the error can be magnified. So keep that in mind. Okay, that's it for now. You might think of other creative ways to use the tangent line, but these are the 3 most common.